Board. Sure. Sure.
What's the worksheet we're working on?
Worksheet, so this is the exam two, review. We'll send it out once we've made some like modifications to it. We have some like slight modifications, we had like 1, 2 problems, so yeah, once that is done, we will send out the worksheets. There's still, if I'm not mistaken, right, there's still a long time before y'all's exam, like it's after spring break. All right, yeah, so we'll send it for sure before spring break. We all have spring break to work on it, unfortunately. Okay, anybody remember what question we left off on? Because the thing he sent me was blank, so, yeah. It was somewhere here. I think 27, 26, something like that. 26, thank you, Sydney. 26. All right, I believe he said this was the first one we would start on. So let's see, 355 milliliter container holds 0.46 grams of neon and an unknown argon at 35 degrees Celsius and a total pressure of that. Calculate the number of moles of argon present. All right, we'll give you all, say, 3 minutes. 3 minutes to do this problem. We'll reconvene at 5:10 p.m. Raise your hand if y'all have an answer. Or Zoom people, give me a Y if you have the answer, or N if you don't. All right, couple N's going through. We'll give you all the time. Like another minute. So the recordings, unfortunately, have not been posted yet because I haven't had the time. So yeah, I'll post more this weekend. Like all the exam 2 review stuff. I have them all saved, I just haven't posted it yet. Yeah, and I know I've been slacking. So, yeah. All right, now y'all have an answer? Still no? All right. Is it like you know what to do or you have no? You know what to do. Okay. Is it like you know what to do or you think you know what to do?
Pretty sure I know what.
All right, when y'all are done, you can work on this. This thing doesn't even work. All right, this is there being a trash can right there. Yeah. Let's toss it up and stick. All right, we're gonna go over it. So 35 or 355 milliliter container holds this many grams of neon and unknown amount of argon, 35 degrees Celsius. And the total pressure of that, calculate the number of moles of argon present. Okay, so what was the first step y'all did? What was step 1? What was that? It was indeed. This is what I like to call the double suck method. I'm not gonna write that down. So you're gonna, what I mean by that is, notice how you're given the stuff of neon, you need to find argon. So what that means is that I'm gonna use PV equals nRT twice. I don't have to use it twice. So in the case of what I'm doing for first one, I know it gives me a total pressure, it gives me a volume, it gives me grams of neon, and R is a thing, and yeah. So what I'm gonna do now is, since it gives me the grams of neon, I'm gonna find the pressure only of neon. So how do I do that? I'm gonna use 1 PV equals nRT expression. Because we have moles, where we can get moles. We have the temperature, we have volume, and R is a constant that we all know. So there is a way to find pressure. So pressure using this equation equals nRT over V. How do we get that? So we have 0.146 grams of neon. Now, how do we get to moles of neon? Molar ratio? Molar mass, yeah. So you divide by the molar mass. And looking right here, the molar mass of neon is 20.18 grams per mole. So 20.18 grams for every 1 mole. So to solve that out, that's 0.146 divided by 20.18. And that gives you 0.00723 That's the moles, so 0.00723. Then R, what's R again?
0.0821.
0.0821. Now what are the units?
Millimeters mercury, right? No,
That's
wait,
a- that's-
that's pressure.
That's pressure, yeah.
Oh, it's, I wrote it down.
There are like 4 units like put together.
Liters times atmospheres over moles times Kelvin.
Yeah, atmospheres, liters over moles Kelvin. That's how I learned it. And then temperature, what is our temperature gonna be? Or it's in Kelvin, what's the number?
35, or the actual number is supposed to be
Yeah,
308.
yeah, so because you just do 273 plus 35, you get 308 Kelvin. And then this all over your volume, what should your volume unit be again? Liters, yeah, because you have liters. If you're ever confused, look at your R. Because your R is in liters, so your volume has to be liters in order for it to cancel out. So solving that out, it's 0.355 liters. I just move the decimal over 3 times to the left. All right, now let's solve this out. 0.00723 times 0.0821 times 308 divided by 0.355 should give me a number of 0.51. The pressure. This is in atmospheres. What I'm going to do real quick is convert it into millimeters of mercury. So what's the conversion factor for that again? For atmospheres to millimeters of mercury? Yeah, you're right on the money, Sydney. 1 atmosphere is 760 millimeters of mercury. Now, some of you might be asking, Rich, why did you convert to millimeters of mercury? Because I saw the millimeters of mercury over here. You could very well convert that number to atmospheres, but I didn't see that at the time. So I just went on my gut instinct and converted to millimeters of mercury. Of course, I'm gonna have to convert back, but we'll cross that bridge when we get to it. So if you do that, we get 391.40 millimeters of mercury. All right, and this is the pressure of neon. So how do we find the pressure of argon? If we have a total pressure and the pressure of neon. There's a certain law you use. Yeah, there's a certain law for that though. Certain guy created that law. So it's Dalton's law. Dalton's law is basically, some people call it Dalton's law of partial pressures. Basically, what he says is the pressure total equals pressure 1 plus pressure 2 ... plus pressure n. So in this case, the total pressure is equal to the pressure of neon plus pressure of argon. So right here we have the pressure of neon and we have the total pressure. So we can find the pressure of argon. So to do that, pressure of argon is going to equal 626 minus 391.4. So 626 minus 391.4. For that, we get our pressure of argon equal to 234.6 atmospheres. Not atmospheres, sorry, millimeters of mercury. Now we're going to convert this back into atmospheres so we can actually use it. So 760 millimeters of mercury is 1 atmosphere. So let's go ahead and divide this by 760 and we get 0.309 ATM. So we're going to use the next problem here. All right, this is where the double part of the sub comes in, the double sub method. So we're going to use our PV equals nRT again to get the moles of argon present. So we know that moles by rearranging the equation is equal to PV over RT. So the pressure 0.309, volume stays the same 0.355, and then R 0.0821 that also stays the same, and same with our temperature, also stays the same 308. All right, so if we solve that out, just multiply all these together, so times 0.355 divided by 0.0821 times 308 to get a number of 0.00433 moles per argon. Now, is that what y'all got as well? Did y'all get a different answer? Those of you who did get that far, is that the answer y'all got? Right. So because you didn't get that far, where did I lose you? Basically, what part did you get up until? Was it like you knew what to do and you didn't do it fast enough, or like you didn't know where to
I
start?
started doing it the right way. I
Mhm.
didn't know about the double sum method thing, so I kind of stopped too early.
Oh, yeah. It's important to like read the problem in that instance, like. If it gives you one and you're trying to find the other one, then you look for. You basically just look at what you're given, so it gives you the stuff to find a pressure for neon, to use it. Then you're gonna plug it back in, subtract. From the total pressure, and then from there, you'll go find your moles of argon. Since you're given a pressure of argon. So it's just using one variable to find another one, I can solve that one. Well, what's up, Daniel?
So when trying to do these problems, do you always start with your PV equals nRT? And
I
then
mean,
you just see which are constant so you don't have to use?
yeah, pretty much that's what I would do. So even if like it's like Boyle's law or something, it's like pressure and volume's changing, like moles are kept constant. So I know to use Boyle's law in that instance. You know what I'm saying?
Yeah, okay, so when you're using, I guess, Charles or Gay-Lussac's, does temperature always have to be in Kelvin when doing the calculations?
Yeah, it does. Your temperature always has to be cold.
Is the same goes for anything else? Like it always has to be an ATM, or that doesn't really matter?
It does always have to be an ATM. Okay, here's the thing, right? For the purposes of this class, it's always an ATM or Kelvin. If you want to go ahead and memorize other R's that have them in like Pascals or like Torr to make your life easier, you can go ahead and do that, but it's just easier to like less memorization on your part. So just keep everything in atmospheric Kelvin because you're required to memorize that R 0.081. Does that make sense?
Yeah.
All right. Any other questions? All right, cool. Let's go on to 27. How many grams of phosphorus react with 35.5 liters of O2 at STP to form tetraphosphorus decoxide? All right, gas stoichiometry. This is one of those problems. All right. This is a question specifically for Taylor. How many liters are in a mole at STP? I know you know it. I said how many liters are in a mole at STP? What's the conversion factor from liters to moles? So at STP, 1 mole equals blank liters. Certain number. Maybe in a certain video. That's close actually. It's actually 22.14. So 1 mole is 22.14 liters at STP. Now that should help you guys solve out this problem. So y'all know where to start or not really? All right, let's go through it. That's all right. So how many grams of phosphorus react with 35.5 liters of O2 and STP to form tetraphosphate oxide? It's 22.14. Is it? Wait, it's 22.4. What am I talking about?
22.414.
Yeah, it should be 4.1. Yeah, thanks, John. Yeah, so 1 mole is 22.4 liters. Honestly, I just use the 22.4. I don't even care about the 4.1. So yeah, 1 mole, 22.4 liters, basically. All right, now you're probably wondering, why is that even useful? Well, let's see. So it gives us liters of O2 and STP to form tetraphosphate dicoxide. The thing is, this thing only exists at STP. At no other instance can you use this conversion factor. So 1 mole equals 22.4 liters only at STP. So say, for example, my pressure was 2 atmospheres and my temperature was 365 Kelvin. Is 1 mole equal to 22.4 liters? No, exactly, because it's not STP. The reason, do y'all want to know the reason why 1 mole equals 22.4 liters? All right, let's go ahead and plug this into PV equals nRT with STP conditions. So we're trying to find our volume, right? So, okay, so Dylan, STP stands for standard temperature and pressure. So what that is basically 1 atmosphere and 273 Kelvin. And yeah, Daniel, you pretty much beat me to it. I was gonna solve out all the equation stuff. But yeah, basically you plug in for 1 mole to solve for volume. So pressure is 1 atmosphere, volume is what you're trying to solve for. Your number of moles is 1, your R is 0.0821, and your temperature is whatchamacallit, 273. So the idea is the volume, if you solve out for that, is 22 liters. That's where that comes from. Anyway, that's not important for this problem. So just memorize that 1 mole at STP is 22.4 liters. So 35.5 liters of O2. And then, as we said from above, 22.4 liters are in 1 mole. Now, where do we go from here? I know y'all know how to do that. And this is 1 mole of O2.
It's the molar ratio.
Yeah, it is a mole ratio. So for every 5 moles of O2, you have 1 mole of that thing, P4O10. But is that the question? That is not the question. Question is, how many grams of phosphorus react? So this is actually 1 mole of phosphorus. That's what we got to change it to. But first of all, before we can even do that, we got to figure out what is our limiting reactant. And here's a shortcut. Oxygen is our limiting reactant. The reason is because the grams of phosphorus that react, if it's asking for that, then it's asking for basically the excess reactant. That's another way of saying that. So basically phosphorus is limiting, or sorry, excess. So what you'll do is you'll convert, so 35.5 divided by 22.4. And then what you're gonna do is divide that one by 5. And then you get an answer of 0.32 moles of P4. And is this the moles of P4 that we started with or that reacted? What was that? Reacted. Why is it reacted? Yeah, because it was the stuff that was used basically, because you converted your oxygen, which you assume to be limiting, to your P4. So 0.32 moles of P4 reacted. right, from there, I'm gonna convert to our grams. So 1 mole is, let's see, this is 31, I think, or 30.974. So 31 times 4, which is 124 grams. So times 124 to get 39.3 grams phosphorus. That we all got as well. 39.3 grams, something like that. What equation did I convert to from PB was RT? So for this problem, or this is for the last problem, so I should just square that off. So for this problem, all I did was to find what the thing, or this is just a relationship you have to memorize, or if you memorize it, it makes your life easier. So 1 mole is equal to 22.4 liters as. Then from there, what I did was I converted into I plugged it into my mole ratio. So to get moles of O2. And then from there, I could figure out how many grams of phosphorus reacted by just saying our oxygen is our limiting reactant. So by that, I can figure out how many moles of phosphorus reacted by converting. So for every 5 moles of O2, there's 1 mole of P4. So I got the amount of moles that reacted. And then from there, I just converted that amount to grams. Does that make sense? Does that answer your question? Yeah. So I found the moles of P4 by using the molar ratio. So as you can see here, I have moles of O2. And then here it says for every 5 moles of O2, there's 1 mole of P4. Does it imply 1 right there? So all I did was just convert over there, and then I got my point P2. And then converted. Does that make sense? All right. Any more questions?
Yes, how'd you know we didn't have to use any of those like equations? Is it because we weren't given enough variables or something?
I mean, that and partially the fact that we're given liters and an STP. So this sort of thing gave it away for me right here. Then I could use the 1 mole equals 22.4 liters.
So how does STP change the question up?
I mean, really, it's like doing the same thing. It's like you're doing the PV equals nRT, but you're not really doing it, you know? Like you plug in for 1 mole, you can do that if you want to, but I'll save you the trouble. It's 22.4 liters when you solve for volume. And then that sort of changes up the question because it's asking for the O2 gas, right? So what you have to do is convert, and then from there you can convert again. Does that make sense?
Yeah.
All right. Any other burning desires?
So anytime it has standard temperature and pressure, do we not use the pervert one?
Anytime it has like standard temperature and pressure, and if it gives you like a liter amount or like a mole amount, then you can use your 22.4 conversion factor. So is there a trick to know when not to use the equation? So I'll just say like look at your problem. Like if it gives you a balanced chemical equation and it has you do something at STP, I'd say use your 22.4 liters. But if it gives you like a pressure and a volume, or like a pressure and a temperature, or like a volume and a moles that like change, then you'd use your equations. Y'all get what I'm saying? Yeah, so balance equation, think this stuff. Sometimes. Right, any other questions? Right, cool. So how many grams of pH 3 can form with 37.5 grams of phosphorus and 83.0 liters of hydrogen gas react STP. So, all right, he gives you a hint here because he's nice, apparently. I'll see that happening. So let's use his other hint. Is phosphorus monatomic, diatomic, or tetratomic? Which one is it? It is tetratomic. So let's write out our equation. So P4, and then hydrogen's what? Diatomic, right? So it should be H2. This is a solid, this is a gas, and then we'll get pH 3. Is this equation balanced? So what do we do to balance?
Or
Or where? Yep, 4 right here. And then what else?
adding
Yeah. So, yeah, that was balanced to me. So can form with 37.5 grams of phosphorus and 83 liters of hydrogen reactants. So what thing do we have to find? We have to find a certain thing.
Limiting reactant.
Yeah, limiting reactant. Yeah, sulfur or limiting reactant. So because that limits, right, how much phosphine we can make. So let's do that. 37.5 grams of phosphorus, P4. But then we got to use our molar mass. So we're going to do 31 times 4 since there's 4 phosphorus atoms. So it's 124 grams of the 1 mole. And then we'll use our mole ratio. So for every 1 mole of P4, there's 4 moles of phosphine. And then we'll go ahead and do the same thing for our hydrogen. So wait, but it gives us liters though. How do we get from liters to moles? And it's at STP. Exactly. So we'll do 83 liters and then 22.4 liters are to 1 mole. And then we have our moles of oxygen from, or sorry, hydrogen from there. Then we'll go ahead and use our mole ratio again. So for every 6 moles of hydrogen, there are 4 moles of pH 3. Now let's solve these two out, figure out which ones are limiting reactant. So 37.5 divided by 124 times 4. All right, we get 1.21 moles. All right, 83 divided by 22.4 times 4 divided by 6. All right, this one's 2.47 moles. All right, which ones are limiting reactant? Phosphorus or hydrogen? Why? Because there's less moles. So this is our limiting reactant. Phosphorus is our limiting reactant. So from there, we have 1.21 moles of pH 3. Now all we have to do is just convert this to grams. So 1 mole is 34 grams. So if we solve that out, yeah, 1.21 times 34. We get 41.14 grams of phosphate. Or this should be a 1. 1. All right. Does that make sense how I got there? Just sort of combines your chapter 4 stuff with your chapter 5 stuff. And by the way, Armand loves these questions. He loves where you can like combine multiple chapters together. All right. Questions on that? So the 34 grams is the molar mass of this thing. So phosphorus is 31, then hydrogen, there's 3 of them, so there's 1. And the molar mass of hydrogen is 1, filled in the periodic table. So 31 plus 3 is 34. That's where that came from. That makes sense? Any questions about that? Any more questions? All right, we're gonna do something real quick. We're gonna skip 29. And that'll be the first one we go over on Thursday. Just because it's more of a complex problem. Like notice here how it says aluminum reacts with excess hydrochloric acid to form aqueous AlCl3 and 35.8 milliliters of hydrogen gas or water. The over water part sort of complicates it because you have to take into account the pressure of the water. So basically, we're gonna skip that and move on to 30. All right. This is some of the good stuff right here. At a given pressure and temperature, or have y'all gone over this yet? Rate of effusion, rate of diffusion. So none of this stuff, the rate A over rate B equals the square root of molar mass of B over the molar mass of A. Davidson did for a little bit. All right, do we have it? This is you to me. Now fuck. Okay. All right. I'm gonna give you all a little bit of an intro. All right. So there's nothing really more to rate of diffusion and effusion than this. All right. Imagine a small hole. All right. So imagine a mouse trying to fit through a small hole. It's pretty easy, right? The mouse is like pretty small and it can fit through the hole quite nicely. Now imagine a cat, like a really like fat cat, like this cat eats like 10 times a day. So this fat cat, imagine this fat cat trying to fit through the hole. It's not gonna fit, right? Or it'll take like a really, like you'd have to like really squeeze it in to fit. And that's basically the same thing with gases, right? So the thing to know with gases is that the smaller the molar mass, the bigger the rate of diffusion. So the thing is, effusion is something fitting through a hole. Diffusion is something coming out of the hole. So effusion is going in, diffusion is coming out. So diffusion. Effusion specifically is fitting something through a small opening. So the smaller the molar mass, the greater the rate of diffusion. That makes sense, right? Smaller gases travel faster in the atmosphere. So there's actually this dude called Graham, right? This is called Graham's law of diffusion. Graham, like graham cracker. So I don't know if he's the guy that made the graham cracker. I don't know. Graham's law of diffusion. And this is basically what it says. The rate A, or the rate of diffusion of one gas over the rate of another gas equals the square root of their two molar masses. It's important, right, that you invert these molar masses. So notice here that it says rate A over rate B. You have to make it molar mass of B on the numerator and molar mass of A on the denominator. See how like A is here on the numerator and then A is on the denominator? That's sort of what we have to do. All right, there's nothing more to it than that. Does that make sense? Yeah, so it wasn't really that bad, right? Yeah, we can definitely do this problem. So at a given temperature and pressure, it takes 4.85 minutes for a 1.5 liter sample of helium to effuse through a membrane. How long does it take for 1.5 liters of F2 to effuse under the same conditions? This is a bit of a tough one. So how'd y'all solve this up? What will be your first step? Or you have no clue where to go from here?
We have to find molar mass, right?
Yeah, that would be a start. So for helium, right, the molar mass is 4.003. So 4.003, and then for F2, it is F2 molar mass is 18.998. So 18.998. All right, which one do y'all want to call A and B? I'm gonna go with helium as B and then fluorine is A. Why is that important? So let's do it. So the square root of 4.003 over 18.998 equals the rate A, the rate of diffusion of A, or the rate of diffusion of B. All right. So to do this, square root it. So 4.003 divided by 18.998. Get that. 0.21. Then we'll square root it real quick. So this is equal to 0.46. So the rate of diffusion of A over the rate of B equals 0.46. And notice here, right? All right, what did I call B and A again? I called B for fluorine. So this is rate of F2, and helium, this is rate helium. All right, so we know how much. All right, so notice here that it gives us liters, right? And then it says at a given pressure and temperature. And wouldn't it just be easier for us to assume that it's at STP? And that make our lives easier? Because we know that 1 mole is 22.4 liters. So let's go ahead and do that. Or wait. So the rate of helium over the rate of F2 equals 0.46. So it takes 4.85 minutes for the 1.5 liter sample of helium to infuse. To fuse under the same conditions. So we found the molar mass rate. So the difference between molar masses here is 0.46, right? So we found the square root of that. So now we need the rate of helium or the rate of fluorine is equal to 0.46. All right, first of all, do you expect the rate of helium to be greater or smaller than the rate of fluorine?
Smaller.
So the rate of helium is smaller. So that means that, yeah, so it'll be greater, right? Because the idea is that large stuff with a smaller molar mass has a greater rate of diffusion. Remember, rate is like how fast something goes. So the helium would diffuse faster than the fluorine, which is precisely what we expect. So here, right, 4.85 minutes and a 1.5 liter sample to infuse to the membrane. So if it takes 4.85 minutes for helium to infuse, so helium we can plug in right here is 4.85. So we're going to say 4.85 over x equals 0.46. Because that's basically the rate. The rate is time in this instance. So what we're going to do is just solve for x. So 4.85 over 0.46. Solve it out. We should get our x. So 4.85 over 0.46. When I solve that out, I get 10.54 minutes. This makes sense, right? Because we have something. It would take more time for the helium or for the fluorine to infuse through the membrane than it did for the helium. So in this case, right, It might be confusing, but what I did was I just set rate equal to time. Rate and time, they don't mean the same thing, but for this instance, time and rate mean the same thing. So when it says rate A over rate B, it's like time A over time B. That makes sense, Deal? Would you all like to try another problem?
Can you like run through the steps that you did in this one first?
Yeah, so first of all, right, I used this equation, rate A over the rate B, it was a molar mass square root of molar mass of B over the molar mass of A. So there I found the ratios between my two molar masses and I square rooted them. So I did 4.003 divided by 18.998, as those are my molar masses, and I got 0.46. And now rate, right, and for the purposes of this, time and rate mean the exact same thing. So the rate of effusion of helium, I just put 4.85 for that, plugged it in. And notice here how I could do that because the samples were the exact same, the 1.5 here and the 1.5 here. So they're both the same amount of gases. If they weren't the same amount, then you'd have to use some like molarity and then convert from there. But they made it nice and easy for you, and they're both 1.5 liter samples. So from there, I said the rate of helium, and then here all I did was I just solved for the rate of F2 using this equation. So 4.85 over F2 is 0.46. Then I just divided both sides, and then the rate of F2 I got to be, where did I put it? 10.54 minutes. And that does make sense because we know to take a longer time for the helium or for the fluorine to diffuse in the helium since that's a larger molar mass. That makes sense? All right. Since you all requested it, one more problem. A sample of an unknown gas fuses in 11.1 minutes. An equal volume of hydrogen in the same apparatus under the same conditions fuses in 2.42 minutes. What is the molar mass of the unknown gas? So whose law do we use again? Graham-Cracker's law, right? So Graham's, Graham's law will we use? So let's do this. The rate of A over the rate of B equals the square root of the molar mass of A over the molar mass. All right, so the molar mass of the unknown gas is what we have to solve. We're solving for the molar mass.
No, you messed up.
Oh, I did. Good catch.
Come on, man.
Yeah. I was making sure you were paying attention. So you
I feel that.
gotta do this. The molar mass of B over the molar mass of A. You gotta switch them up. Why? Because Graham said so. Go blame the box of graham crackers you have at home. Anyway, so Graham's law. Rate B equals rate A. Rate A over rate B is molar mass of B over the molar mass of A. So here we have a sample of an unknown gas fusing in 11.1 minutes. Let's make the unknown B. Why? Because unknowns are beta. I don't know. So I'm just gonna pick, like, really that's all you have to do. Just make one of them A, one of them B, but be like consistent. Don't flip them. What I mean by that is that I'm gonna make the hydrogen A, right? So it's 2.42 over 11.1. So notice how this is A and this is B. Now I gotta not flip them. So I gotta make this the molar mass of hydrogen on the bottom. And this is the molar mass of H2. So it's gonna be 2 grams per mole. And then this is X. This is what we're trying to solve. All right, from here, all we have to do is just algebra. So 2.42 divided by 11.1, we're gonna get 0.22 equals square root of X 2. And then we're gonna square both sides right here to get rid of the square root. So we're gonna square both sides. And then we get 0.0475. And that's gonna equal our X over 2. So now we're gonna multiply this by 2. And we get our molar mass is equal to 0.0951 grams per mole. And you're probably like, no gas exists on the periodic table like that, but this is all theoretical. So yeah. Let me just make sure it's right. Graham's law. Rate 1 over rate 2 is square root of 1 mass 2 1 mass 1. Yeah. All right, so I got 0.0951 grams. Does that make sense?
Is there a problem like number 30 where the liters are not the same?
Problem like number
Volume.
where the liters are not. There are not. There is not. This is chapter 5. I think this is like one of the last things in chapter 5. So there actually isn't one where they're the same. Actually, you have to use Gen Chem 2 stuff to find out if like when they're not the same. Because you have to do like Rice tables and stuff like that, equilibrium. All right, but this makes sense. Does that make sense on how I got that number? Specifically? All right. This. Well, let's try switching these, see if I get the same thing. What was it? 0.0951. Rate A over rate B, square root of more mass than B over more mass A. That's basically all I need to know for Mr. Grant for. All right, this is gonna be the last, or let's do number 10, or number 33, sorry. So how do you convert 10 atmospheres to torque? So 1 atmosphere is how many torr again? Yeah, 760. So you'll get a grand total of 7,600 torr. All right, nice and easy problem. All right, let's go back to 32. Does SF6 boiling point that at 1 atmosphere behave more ideally at 150 degrees Celsius or at 20 degrees Celsius? So have y'all learned like when gases deviate from a higher or ideal behavior? No? Okay. So gases deviate at lower temperatures and higher pressures. Basically. Why is this the case? So what does a gas need to do that's ideal? Or what makes a gas ideal?
They don't interact.
Yeah, there's no forces between them. There's no attractive forces between the container. That's basically it, right? There's more stuff, but like there is the okay, yeah. Let's write a bit more. I got that doctor handwriting from the get-go. So deviate at put this in all caps. Lower temps and higher pressures. All right, so higher pressures, right? This is pretty easy to explain. So at higher pressures, chances are the molecules will be colliding more frequently, right? So at higher pressure, since they're colliding more frequently, they have more chance to interact with each other, which is precisely what you don't want in an ideal gas. Interactions with the container and interactions with the walls of the container and the interactions between, the stuff, molecules themselves. Now, lower temperatures, it's actually the same thing. So at lower temperatures, right, gases are prone to move more slowly. So if they move more slowly, that means that what? They're more likely to stick together. Because at lower temps, they behave more like solids or liquids. That's when they'll deviate from their sort of ideal behavior, their ideal gaseous state. All right, anyway, bit more conceptual stuff to think about. So, yeah. Y'all have any questions about any problem we went over today? All right. In that case, y'all are free to head out of this.
Yeah, I got a small question real quick.
Also,
So when it comes to all of these problems, there's like two equations, right? If nothing changes and if something does change,
yeah, pretty much.
and then if nothing changes, it's just the PV equals nRT.
Yeah, if nothing, or wait. What do you mean? Like, if nothing changes or everything changes?
If nothing changes,
So if nothing changes, right, that'll actually be your like. You're talking about something like this, right? You have a problem, it'll say like 5 atmospheres, 15 liters, moles or whatever. It depends on what it gives you, to be honest. Like, and it gives you all of them, like a pressure, a volume, moles, and like they all like sort of change. Then from there, you use your PV for that. But I get what you're saying though. Like, I get your thought process in that you think they don't change. Basically, what you do is like you do what's given. So basically, if there's like a pressure and a volume and none of them change, then you'd use your PV as nRT. However, if it does change, like say a pressure and a temperature change, then you'd use like one of the other laws. Does that make sense?
yeah.
All right.
Mhm.
All right. Any more questions, Zoom people? Next session, yeah, it's Thursday from 3 to 4.
All right, thank you guys. I'll catch you.
That was it. Right, like, subscribe, do all that good stuff for the YouTube algorithm. I'm still done a while. All right. Y'all have any more questions? Feel free to stick around. Otherwise, I will see you all on the flip side. Yeah, this is the exact same review we're gonna do. Basically, it'll be this till we finish it. Like, there's still a lot more pages left. All right, catch y'all later.